welcome everyone to our next session with Dr. William Bahnfleth. All right, the kind of future of commercial real estate related to our post-COVID ventilation requirements. Let me just start by giving a brief introduction here. Dr. Bahnfleth is a professor of architectural engineering at the Pennsylvania State University. He held previous positions as senior consultant for ZBA Incorporated in Cincinnati and principal investigator at the U.S. Army Construction Engineering Research Lab in Champaign, Illinois. He holds BS, MS, and PhD degrees in mechanical engineering from the University of Illinois and is a registered professional engineer. At Penn State, Dr. Bahnfleth teaches undergraduate courses in HVAC fundamentals and system design, as well as graduate courses in district cooling systems and indoor air quality. His research interests cover a wide variety of indoor environmental control topics, including chilled water pumping systems, stratified thermal energy storage, protection of building occupants from indoor bioaerosol releases, and ultraviolet germicidal irradiation systems. He's the author of, or co-author of, more than 170 technical papers and articles and 14 books and book chapters. Bill is a fellow of ASHRAE, the American Society of Mechanical Engineers, and the International Society for Indoor Air Quality and Climate. He served as president of ASHRAE in 2013 to 14, and his ASHRAE honors include the Louise and Bill Holliday Distinguished Fellow Award, the Campbell Award, and the Paul Anderson Award. And with that, I will turn it over to Dr. Bahnfleth.
Hey, thank you for the introduction, Larry, and thank you for inviting me to speak here. Let me put my slides up and we'll get going. So my talk today is about where ventilation standards may go in the future after the pandemic is over, and I've divided it up into three main sections. I think in order to understand where things might go, we have to know where we're starting. So I'll give you some background on where ventilation standards are today and what they do for us. And then quite a bit of the talk will be on the experience during the pandemic of trying to modify the operation of HVAC systems to reduce infection risk. And then at the end, I'll do some speculating about what the lessons learned from that experience may result in terms of changes to our most common ventilation standards. So let's begin with the background and status quo. In the United States, the main ventilation standards that we use are three that are developed by ASHRAE under the American National Standards Institute process. ASHRAE standard 62.1 applies to non-residential, non-healthcare buildings. 62.2 applies to low-rise residential buildings and other residential occupancies as well. And 170 applies to healthcare. 62.1 and 62.2 are quite similar in many respects. 170 is different, but we'll mainly be talking about 62.1 in this brief talk today. So before we go any farther, it might be a good idea just to refresh on what the word ventilation means. And we could first look at the standards themselves. Standard 62.1 defines ventilation as the process of supplying air to or removing air from a space for the purpose of controlling contaminant levels, humidity, or temperature within the space. 62.2 says it's the process of supplying outdoor air to or removing indoor air from a dwelling by natural mechanical means. It doesn't actually say anything about the purpose. And interestingly, Standard 170 2017 doesn't define ventilation at all. But as the term is normally used, we're referring to replacing indoor air that is contaminated to some extent with cleaner outdoor air to control the air quality. So now that we have a common understanding of what ventilation is, we have to consider what it means to have acceptable indoor air quality controlled by ventilation. And there are a list of possible criteria that we could use to define acceptability. One is safe exposures to contaminant gases and aerosols, particles and droplets that we may find indoors. And certainly all ventilation standards have that objective. Another is perceived air quality. So how do the occupants feel subjectively about the air quality? That's explicit in standard 62.1 and 62.2. It's implicit in standard 170. This mainly means controlling odors. Of the three standards that are commonly used in the US, only 170 actually addresses infection control, or asepsis as it's called in the statement of purpose of that standard. So 62.1 and 62.2 have no explicit goals of reducing infection risk. We could also cite productivity and health, as were discussed in the keynote, as possible goals, but in terms of minimum standards, the ones that determine what our building codes look like, we don't have that yet in any of them to my knowledge, and certainly not in the three standards that we're discussing here. So how does a standard like 62.1 or 62.2 define acceptable air quality? I've put the definition from 62.1 up on this slide and highlighted the most important things, and these key back to what we just looked at on the previous slide. It's defined as air in which there are no known contaminants at harmful concentrations as determined by cognizant authorities, and with which a substantial majority, 80% or more, of the people exposed do not express dissatisfaction. So they're highlighted in red as that safety criterion, and in blue, the acceptability criterion, and that's it. Infection control isn't addressed, and actually the contaminants that we're thinking of in this standard are gases and particles, and not microorganisms either. And that's an important factor, of course, with respect to the pandemic. So with that definition, how do we actually define the ventilation amounts that are required? And this ties into research that was done in the last century, a lot of it in Denmark, some of it in the US and other places, to determine what ventilation rates per person would result in an acceptance level that was deemed appropriate for exposure to bioeffluent, to the metabolic products that we all put out. And the work of Fanger, which is summarized in the figure on the right, tells us that it takes about 7.5 liters per second per person, or about 15 cubic feet per minute per person who's unadapted, to have 80% acceptance of the odor levels. And so that's one of the main factors determining our minimum ventilation rates. The other is the response to building emissions, which can be treated in somewhat the same way. So in 62.1 and 62.2, the concept is that we have to ventilate a certain amount per person for bioeffluent, and a certain amount per unit of floor space for building emissions. And that's really a different concept than we see in health ventilation standards, where air changes that are not directly tied to the number of occupants are used. So there we are, 15 CFM per person, more or less. But it's important to note that over a couple of centuries, we've seen these minimum ventilation rates go all over the place. In fact, if we go back to the early and mid 1800s, and come forward to today, we've been everywhere between 5 CFM per person and 30 CFM per person, depending on the prevailing attitude about what we were trying to accomplish with ventilation. Is it ventilation for health? That got us to 30 CFM per person in the late 1800s and early 1900s, about the time of the influenza pandemic. Odor control takes us to lower levels, as we've seen, and severe concern, over concern for energy conservation has gotten us to those numbers as low as 5 CFM per person, which is not that long ago. In the US, that goes back to the oil embargo and the energy crisis that was related to it. So we have minimum ventilation rates today, but they may be different again in the future, and may be quite different. But one thing we do know, and this was mentioned in the keynote presentation, is that our minimum standards really are not particularly good in terms of the outcomes for the occupants. That we have a lot of evidence that there are unrecognized, unrealized health and productivity costs or benefits associated with these ventilation levels. And the two figures here come from studies that have summarized multiple studies that have looked at the effect of ventilation rates on, in one case, sick building syndrome symptom prevalence on the left, where we see that if we go from current minimum ventilation rate of 7.5 liters per second per person, roughly, and double that or triple that, we get significant reductions in reported sick building syndrome symptoms, which presumably translates in some way into productivity and absenteeism impacts. And on the right, we see task performance versus ventilation rate data, and it shows, as was referred to in the earlier presentation today, the potential for perhaps as much as a 3 or 4% improvement in productivity. Again, if we go from our current 7.5 or so liter per second ventilation rates to 2 or 3 times that amount. So there's a lot of room for improvement with respect to those metrics, but this is where we are. Although 62.1 and 62.2 and 170 are titled as ventilation standards, they also deal with filtration for particulate matter, and particulate filtration requirements are specified in terms of MERV ratings based on ASHRAE standard 52.2. The typical mechanical filters that are used in our buildings have performance curves like the ones you see on the right in this figure. They tend to have relatively high efficiency at large particle sizes, and then a dip in the middle, and high efficiency again at small sizes due to the mechanisms of removal. I superimposed on this figure the 3 ranges within which the performance of a filter is rated by standard 52.2, 1, 2, and 3 there, from 0.3 to 1, 1 to 3, and 3 to 10 microns. So in our minimum ventilation standards currently, we require in 62.2 a MERV 6 filter or better, and in 62.1 MERV 8 or better. And we can see from this table that comes from the standard that neither of them is particularly good for finer particles that might be associated with health effects. They're moderately good to good for the 3 to 10 micron particles, but not very good at all for lower particle sizes. So if we want to do something about health, as we'll see, we really need to look a lot farther up the scale for filter performance. As the numbers get larger, the filters get better. And MERV 13 has been for some time identified as a good target for filtration if you want to have high performance indoor air quality. Why is that? Well, we can think of our respiratory system in a way as a filter. On the left of this slide, we see a respiratory deposition fraction versus particle diameter curve. It looks a little bit complicated at first. The solid line is the head airways deposition. This is in the nose and mouth and the upper part, the outdoor air intake, if you will. And you see a lot of particles removed at large sizes there. But we're really concerned more about the alveolar region, the small dots that we see, the line labeled ALV. And what we notice there is that there's almost no deposition there in the head airways and low effectiveness, or low deposition of the larger particles in region 2 and 3. But the most important thing here is to look at the filter efficiencies that we use to remove particles from the air and how they relate to these respirable particles that wind up deep in the lungs. And we see that MERV 6 and 8 filters have very little ability to stop those particles that have health effects from getting to where they can do damage. If we do an analysis of the impact of better filters on healthcare costs, morbidity and mortality, we wind up with results similar to what we see in this research by University of British Columbia. Here we're looking at the per person annual benefits of removing fine particulate matter from the air as a function of the MERV rating of the filter. And this is shown for a number of different outdoor air profiles. So everything from Delhi and Beijing, some of the worst in the world at the top, to clean Vancouver and Sao Paulo at the bottom. And we have benefits for MERV 8 filters that are no more than about $100 per person per year, and we're getting 6 or 7 times that amount when we replace those filters with MERV 13 or 14, because those filters are removing those fine particles and keeping them from doing the damage that they can do when they deposit deep in our respiratory system. So this is the benefit that we're leaving on the table by having really low performance filters in our systems. So that's the status quo. Now let's go on to the COVID experience here. Everyone probably has heard by now that the WHO and CDC positions on transmission have shifted to acknowledge that transmission by the airborne route indoors occurs when there's prolonged exposure and poor ventilation in the space. So we now have their backing to focus on controlling airborne exposure, and that means mostly controlling respiratory droplets. Respiratory droplets are the droplets that are produced whenever we're speaking or singing or breathing or doing any other activity that involves exhaling. And these droplets are mostly smaller than 10 microns. The peak frequency is down around perhaps 2 or 3 microns in size. And those particles are all inhalable and respirable, and they may contain 50 to 90% of the viral load. So, and they can also stay in the air for a long time. So this is what we're trying to control. When we want to reduce the risk of COVID-19 to an acceptable level, how do we do that? Well, we don't have great tools for doing it, but we do have the Wells-Riley model developed by researchers at Harvard School of Public Health. And this relates probability of infections to the amount of infectious material that's being put into the air, number of infectors times infectious quanta on the right-hand side, and the ventilation rate and exposure time of the susceptibles in the space, so the amount that's being taken in. And we can decrease the probability of infection by increasing the uncontaminated airflow rate, which lowers the concentration of quanta in the space. So this can be used as a way of determining what uncontaminated airflow rate is needed to achieve a certain level of risk. And we do have infectious quanta numbers, although fairly uncertain for SARS-CoV-2, and these are being used to develop recommendations for air change rates to reduce infection risk. Very important part of the approach to risk management. So by applying the Wells-Riley model, we find that for some occupancies, perhaps for school classrooms and for offices, that 5 to 6 air changes per hour would be a good level, and 3 to 4 is considered to be at the low end of the scale in terms of acceptability. The important thing here to note is that this is quite a bit higher than the outdoor airflow rate that we have in most buildings because of the minimum standards that we use. So this is one of our main tools. An important extension of it is that we can view the performance of an air cleaner or a mechanical filter in terms of its air changes per hour. So we can view that flow rate Q in the denominator of the argument of the Wells-Riley equation as being not just outdoor air, but also the effects of filters and air cleaners and even deposition and decay due to changes in temperature and humidity. And this brings us back to the question of filters and their performance and why the minimum filters in 62.1 and 2 are not acceptable. And so here I've overlaid the rating size ranges of those filters, of MERV filters, on the respiratory droplet spectrum. And what we see is that MERV 6 and 8 filters do very little in the 3 micron and under range, where most of the particles of concern are. And that's why we need to go to a MERV 13, which is 50% or better for 0.3 to 1 and 85% or better for 1 to 3 to get the effect that we're looking for. And to tie into what I just said about equivalent uncontaminated airflow, we have a choice. Do we have more ventilation or do we have better filters? And this figure from a paper evaluating influenza risk by Azimi and Stevens from a few years ago shows pretty clearly that we can get a reduction in infection risk, at least as predicted by Wells-Riley, much more cost effectively by increasing the rating of the filters than by increasing ventilation. The solid curves with the locations on them are the cost per year to achieve a level of risk reduction with ventilation, and the black curve with the MERV ratings on it is the filter curve. And we also notice here that this curve bends pretty sharply at MERV 13, which means that we're paying more for more efficient filters, but not getting a lot of performance. And that's why MERV 13 is the recommended filter efficiency goal in ASHRAE and other guidance. So some observations on all of this. Our buildings designed to minimum standards don't have enough ventilation for infection control. We know that increasing outdoor airflow can be not only expensive, but difficult. Demand-controlled ventilation during the pandemic is something that isn't really a virtue because it reduces the ventilation rate and increases risk. We can see that the filters that are required by our minimum standards aren't effective against infectious aerosols, which is why we're recommending increasing efficiency. And we won't talk about it in detail because of the time constraints, but air cleaners can be effective supplements to ventilation and filtration. But unfortunately, and maybe this is something for discussion, there are a lot of poorly characterized air cleaner technologies out there, only a few that we can really rely on. So there's bad news and good news. The bad news is that non-healthcare buildings aren't well protected and that we need upgrades that have some associated costs. But the good news is that the upgrades contribute to better indoor air quality in a number of ways, and the value of that is enormous, as has already been discussed today. And so there is a sustainable path to better IAQ by combining different controls. So that's about all I'll say about COVID-19, but I do want to point you to the ASHRAE website where our guidance is. It's ASHRAE.org/COVID-19, and there are actually hundreds of pages of guidance on COVID-19 risk mitigation for airborne transmission there, as well as a lot of other resources. And although there's hundreds of pages there, we realize that can be hard for many to go through. So we've just published or approved a set of what we call core recommendations for HVAC, and I've put them all in a paraphrased form on this one slide. Follow public health guidance. Wearing masks is important even if you have good HVAC engineering controls, because it reduces the source emissions and also to some extent your exposure if you're not infected. For ventilation and air cleaning, at least code minimum outdoor air, because we need that for general air quality control, but you don't need to try to maximize it. It is important to have MERV 13 or better filtration for particulate matter. And we can supplement that in a number of different ways. Air cleaners, standalone filtration units in individual rooms. How do we know whether we need to do that or not? We can use Wells-Riley model-based analysis or other infection risk analysis to determine what combinations of controls will be effective. There are also some system operation considerations that are noted here as being fundamental. Maintain temperature and humidity set points. We don't feel strongly that it's necessary to humidify buildings that aren't humidified, although there is a benefit there. But there are many downsides to humidification in some situations as well that make it hard to make that a blanket recommendation. Systems should ventilate to their designed level during all occupied periods. So this implies no demand controlled ventilation and keeping the system on when the cleaning crew is there, as well as the people who may work in a building. We can flush spaces between occupied periods to reduce residual contamination. It only takes about 3 air changes to do that. So we have an efficient way of determining when we've cleared a space properly. And we should design and operate our systems to minimize reentry of contaminants. And the final thing, which is very important, is commissioning of systems to verify that they're operating as designed. The GAO published a report earlier this year that reported that 41% of school districts in the US had 50% or more of their HVAC systems in need of significant repair or replacement. If we would just fix systems, we would be a lot better off in terms of air quality, and we would probably also save enough energy and energy cost to cover the cost of a lot of these improvements that we're talking about. So that's highly recommended. And so now to the future, and then a little crystal ball gazing. And to some extent, your guess is as good as mine, but here are a few thoughts that I have about where we might be going. First of all, I think that the future is a improved definition of what acceptable air quality is. And I think part one of that is health and wellness. The benefits of having better air quality have been there for all to see for quite a while, and it's been a real struggle, though, to communicate that outside of the indoor air quality community that I've belonged to. But I think we're finally getting somewhere with the idea of healthy buildings and wellness. So that's one thing. The second is to consider occupants and indoor air quality as something that connects to the concept of resilience. So an epidemic is an unusual event that endangers the operation of a building and the ability of occupants to be in it. So we should consider that an aspect of resilience. And then we also have ambient air quality emergencies like wildfires that have affected the US this year and Australia, and that also come up seasonally in Malaysia and Singapore when fields are burned. So we don't have that in our standards now, but I think it's going to be there in some form in the future. We're also going to have to connect our air quality standards with the idea of sustainability and not just health and resilience. And I've listed here a lot of ways that we might go about achieving that. Flexible operation, the ability to change fairly drastically the operation of a building from the point of view of air quality control when necessary. Using all of the efficient ventilation techniques that we have at our disposal. And really importantly, I think alternatives to ventilation, better filters and air cleaners. We need a lot of development there, but that's going to help. And then finally, connecting all of this with smart building concepts and using sensors so that we're not delivering high indoor environmental quality where no one is present. I think we have a lot of ability to reduce the energy use of buildings at the same time that we're increasing the level of IAQ. So to summarize that with respect to the standards, I think in ventilation standards, we will see significant increases in minimum filter efficiency. MERV 13 has already become something of a de facto standard for those who design buildings that are considered to be of high quality. And in California, it's the law, Title 24. I think we may see increases in minimum ventilation rates. I think there will be a lot of pushback on that, but I think it can be done if it's done in the right way. I think we'll see explicit procedures for using air cleaning and performance-based compliance paths. We have the indoor air quality procedure in ASHRAE standard 62.1. It implies that you can use air cleaners, but leaves it to the user's imagination how that could be done. And as I said before, resilience requirements showing up in these standards that aren't there now. There will be interactions also with energy standards. I think we'll see more attention to requirements in energy standards that relate to providing better indoor air quality. Filter rating standards need some work. We've learned from the pandemic that 52.2 isn't as great a standard as we might have thought it was in some respects. And we need a lot of work on air cleaner methods of test that don't really exist today that allow us to compare ventilation, filtration, air cleaning on a level playing field kind of basis. So final thoughts, just to summarize, our current minimum standards set a bar for indoor air quality that's too low. We've learned through the pandemic that infection control is yet another weakness, shortcoming of where we've set our IAQ standards, but it's also had the beneficial effect of doing a lot to raise awareness of the importance of IAQ. I think that resilience and wellness are synergistic trends that they're going to work together well in advancing our standards. And the last thing I'll say is that we have to be careful that IAQ doesn't go back to its old place once the pandemic ends. I saw that happen with concern about bioterrorism 20 years ago. We did a lot of work on how to protect buildings from anthrax, and it all came to naught after there were no more anthrax attacks because the motivation to spend the money to change the way we do things was lost. I think that because of the effect of the pandemic, that's not going to happen, but we need to be aware that that's a possibility. So with that, I'll conclude, and I'll be happy to take questions and comments with the time remaining.
Okay. Bill, before I start in on the questions, I just wanted to clarify the core recommendations for HVAC that you showed. Those
Yes.
are, or are those primarily for the commercial sector?
Those are supposed to be recommendations that are applied across all the non-healthcare occupancy types that we deal with, but they would apply very specifically to commercial buildings. They're probably more completely than any other type.
Okay. First question here, right, relates to UV light as means for decontaminating the air, right? Any thoughts on that?
UV is the one air cleaner type about which at least we in ASHRAE have no question that it works. It has a very long history of being studied and applied. It was used effectively to stop measles outbreaks in schools in the 1930s in the Philadelphia area in some pilot studies that were done by Harvard School of Public Health. So we've been using it for a long time. And it's approved by the Centers for Disease Control for tuberculosis control as an adjunct to filtration. So NIOSH has actually published a design guide on upper room UV systems. It's is really the next best technology, or the next in line after ventilation and filtration to control infection risk.
And speaking about healthcare, right? This question, what about increasing negative air pressure in buildings as is done in hospitals?
Well, airflow control is important, certainly. That's an important principle in healthcare design, flow from clean to less clean, and making sure that we're not moving contaminated air from a place where maybe there's a sick person to where someone who's susceptible would be exposed. So that's important. It's important in laboratories design as well. The problem with pressurization and other types of buildings is that they're not necessarily designed to be pressurized, and it's not very easy to do that. But where that concept can be applied, it can be useful. If you look at the ASHRAE residential guidance, you'll see that there is some discussion there about what do you do if there's someone in your home who's got COVID and you want to isolate them, and it discusses the idea of setting up a space as a negative pressure room to avoid contaminating the rest of the home. So all these principles can be applied to many different types of facilities. Air distribution we've not done so much with now because it's hard to change the air distribution that a building already has. It's probably the least changeable parameter in the building. But I think in the future, after the pandemic, when we look at changes to standards and changes to best practices, that we may see some differences in air distribution as well.
Here's a question about, again, motors and fans, right? By increasing the MERV ratings of the filters, right, aren't we going to put more strain on our fan motors? And what options might there be, right? Would we need to change out the motors along with the filters to be able to handle that higher requirement?
Well, that's certainly a reason to not do something that comes up when you say filters should be increased in efficiency. And it's possible that there will be enough change in the flow resistance of a filter when you change from whatever you've got to something like a MERV 13 that it doesn't seem like a good idea. It's either putting too much strain on the motor or it's reducing airflow. But actually, there's quite a bit of variability in the pressure drop through filters of different MERV ratings, and it's not too hard to find a filter that has a higher rating that doesn't have too much of a change in pressure drop, as long as you're staying down in the range that we're talking about. And there are other creative options as well. If you happen to have pre-filters and final filters in a system, someone I've worked with who has been looking at this a lot has suggested that 2 MERV 11 filters in series come pretty close to the performance of a MERV 13. So if you've got 2 racks and can put in a higher quality pre-filter, that may help. And this is also where air cleaners come into play. That if you can't upgrade the filter efficiency to where you would really like it to be, then UV could be added in your air distribution system, or you could consider in-room measures like standalone air cleaners. That's really I think the great thing about this approach of focusing on what is the total equivalent clean air flow that needs to be delivered, because it gives you the flexibility to live within those limits of systems and still get to the level of risk mitigation that you would like to have. And in the future, of course, with new systems, of course, we can design systems to have the same pressure drop they have now with higher efficiency filters. It just means changing filter rack configurations or changing airflow rates. So these are mostly retrofit issues that we're talking about here.
Yeah. A couple of questions, again, related to alternate air cleaning methods. Can you speak about bipolar ion generation, or also Phi cells as a COVID mitigation solution? Hope I
I'll have to
pronounced
admit,
that correctly.
I've never heard the name Phi cells before. There's a whole class of air cleaners that we generally call reactive species air cleaners, ion generators, photocatalytic oxidation, dry hydrogen peroxide, some call their product plasma. All of these air cleaners put things into the air that are supposed to either inactivate, primarily inactivate microorganisms, destroy them by oxidative processes. In the case of ionization, also to increase particle removal rate from the air by causing them to agglomerate. You put charges on particles, they stick together and get bigger, and they deposit more readily. So that's the class of air cleaners that we would really like to see understood better, and it doesn't have the kind of evidence base behind it that UV does, and that raises concerns both about effectiveness and about safety. And I hate to just raise doubts, but we saw what happened with ozone 15 years or so ago. It was widely touted as an effective odor controller and air cleaner, and it is. Ozone's a great disinfectant. It's just not very good for people, and it was found that you couldn't have effective levels of ozone for disinfection and odor control that were safe for humans. And we could ask the same questions about putting hydrogen peroxide gas into a space that's very oxidative. So there's just there are a couple of general questions here that need to be answered by research about safety, and also the effectiveness question. We don't have a level playing field way of comparing some of these different air cleaners. And when you translate something like the amount of time it takes to get, say, a 99.9% reduction in airborne concentration with an ionizer or dry hydrogen peroxide or some other air cleaner, you translate that into an air change rate. Sometimes it actually doesn't look very good compared to just having a better filter in the system or having a little more outdoor air. So I'd like to be able to be more positive about those sorts of air cleaners, but there's really just some knowledge gaps there that I think need to be filled, and we can't do that instantly.
All right. Well, I'm so sorry that I have to call time on our session now. I would like to invite everyone to join a small group discussion tomorrow regarding post-COVID ventilation, which will be led by Paul Ehrlich. Dr. Bahnfleth, you're certainly welcome to join us if you have time available then. And just a reminder, we do have a Meet the Speaker chat room. Go to the chat button on your navigation bar and look for a chat room that's marked Meet the Speaker. Again, thanks for all the questions. We'll try to get these answered by Dr. Bahnfleth and then forward those answers back to all of you. Thank you so much, Bill. Much appreciated. Any final thoughts?
No, I don't think I'd add anything else. I do hope I can find the chat room here. I'm looking at the button right now. If I don't show up there, I'm waiting here trying to get in.
Okay. Okay. All right. Thanks again.
Yeah. Bye-bye.